Dear students, welcome to another lecture on structural analysis on mechanics of solids. We are continuing with the analysis of short columns. So we are dealing with direct as well as bending stresses on short columns. So here we are going to do a numerical related to the concepts that we learned yesterday. So here what we have is we have a rectangular cross section 400 mm by 150 mm by 300 mm, and there is a load 120 kilonewton acting at a distance, radial distance 50 mm from uh, the point. So the first thing what we require is we require eccentricities from the x and the y axis. So if we apply some trigonometry, we will see that. So what we can do is we can redraw this diagram. So if we try to redraw the diagram, this is XX and this is YY. So we have 150 each here in mm and 200, 200. So if we apply trigonometry, we will see that the eccentricity from the y-axis comes as 40 mm and the eccentricity from the x-axis comes out as 30 mm. And the load is 120 kilonewton. P equals 120 kilonewton. Now, the very first thing we need to do is we need to mark the sign of the stresses in all the four quadrants. So we are having four quadrants. Let us call this as quadrant number 1, and this is quadrant number 2, this is quadrant number 3, and this is quadrant number 4. So here let us start with the moment about the x-axis. So moment about the x-axis, if we are applying a moment at the about the x-axis, the moment will be like this, and because the eccentricity is on this side and the load is acting downward, the moment would be like this. The top half would be in tension. Okay, the top half would be in compression, and the bottom half will be in tension. So for compression we will be using the positive sign, so we are going to have a plus here, we are going to have a plus here, and we are going to have a negative sign here, and we are going to have a negative sign here. Now let us consider the force about the y-axis, the moment about the y-axis. So as you know, since it is towards the right, the bending moment will be like this, and the right half of the cross section will be under compression. So here again, due to y you will have positive, here also due to y you will have positive, and you will have negative on this half. Okay, so now the sign of the various stresses have been done. The next step is we need to calculate the stresses that are going to act at the point, each of the points A, B, C, D. So let us write the equations for that. So the stress at the point B will be equal to sum of the direct stress, so there will be direct stress, plus sum of the bending stress at B, there is going to be bending stress, there is going to be bending stress, let us call it as sigma B, due to moment about the x direction at the point B, plus bending stress due to moment about the y-axis at the point B. So what we have to notice is these two plus signs are coming in the equation because we are having two pluses here. Okay, now let us try to write the equations for that. So as you know, the direct stress is nothing but the load divided by cross-sectional area, so that is W divided by A, plus the bending stress about the x-axis. So bending stress due to moment about the x-axis means what we have to do, that is going to be the moment about the x-axis, that is going to be W into E. The magnitude of the moment about the x-axis is W multiplied by E. So we only have to write the magnitudes. divided by Ixx. Ixx means the moment of inertia about the x-axis. So that is Ixx into the uh, into Ymax. Ymax is going to be the distance of the point B from the x-axis. The distance of the point from the x-axis is B is at a distance 150 mm from the x-axis. So into 150 mm into 150 mm. Now again plus we have the moment about the y-axis is going to be, so here the here let us put eccentricity from the y-axis as Ey. So Ey divided by, it is going to be Iyy here, multiplied by the distance from the y-axis. Distance from the y-axis for the point B is 200 mm. It is going to be 200 mm. So this is the equation for the um, bending moments. So what we can do is we can substitute the various values. So if we substitute the various values, what we can see is 120 into, let us put everything in Newton and mm, divided by 400 multiplied by 300 plus 120 into 10 raised to 3 multiplied by Ex. Ex is the bending moment about the x-axis, the eccentricity from the x-axis, that is 30 mm, divided by Ixx. Ixx is BD cube divided by 12 about the x-axis, that is 400 into D cube. D cube is going to be 300 cube divided by 12. So that is Ixx multiplied by 150 plus again 120 into 10 raised to 3 multiplied by the eccentricity about the y-axis is 40 mm multiplied by the distance is 200, the whole divided by Iyy. Iyy is going to be 300 multiplied by 400 cube divided by 12. So if we do these calculations, we are going to get the value of the stress at the point B as 2.2 plus 2.2 Newton per mm square. So this is going to be the value of the net stress at the point B. Now if we notice something, this is the general calculation that we have to do for any point. These equations are valid if you want to find the stress at any point. Okay, you want to find the stress at any point, these equations are going to be valid. However, if we want to find the if you look into this particular problem, the numerical value of the distances from the x and y axis of the point B, C, D and A are going to be the same. The numerical value of the stresses are going to be the same. What that means is numerically sigma Bx, that is bending about the x-axis of the point B, is going to be same as sigma bending stress about the x-axis of the point A, that is also going to be same as the bending stress of the point C about the x-axis will be same as bending stress of the point D about the x-axis, because all the 4 points, okay, the numerical values are going to be the same, the magnitudes are going to be the same, because all these points are located at a distance of 200 mm from, no, there is a slight mistake. um, okay, there is no mistake, all these are located at a distance of 150 mm. Okay, all these are located at a distance of 150 mm from the x-axis. So for each of them we don't have to do this repeated calculations, we just have to find the numerical value of one of them once, and once we know this numerical value we can use them again and again. So what we can do is let us find the numerical value of this particular term, that is this particular term. Let us find the numerical value. So that is 120 multiplied by 10 raised to 3 into eccentricity is 30 mm from the x-axis, the whole divided by 400 into 300 cube divided by 12 multiplied by 150. So the magnitude of this stress comes out to be comes out to be 0.6 Newton per mm square. So this comes out to be 0.6 Newton per mm square. So this is the magnitude of this stress. Now similarly, let us calculate the magnitude of the similarly, if you try to see the point, the bending stress about the y-axis of the point A is going to be same as bending stress about the y-axis of the point B. This also will have the same magnitude as bending stress about the axis y of the point C, same as bending stress about the point y of the point D, because all these points A, B, C and D are at a distance of 200 mm from y axis. So if we try to find the numerical value, what we can get is 120 into 10 raised to 3 into 40 divided by the I is 300 into 400 cube divided by 12 multiplied by 200. So the magnitude we are going to get, and this value is going to be, again it is going to be 0.6 Newton per mm square. So this magnitude is also going to be 0.6 Newton per mm square. 0.6 Newton per mm square. So now we have the magnitude of the stress, and as you know, the direct stress value, if you calculate uh, the sigma d value, if you calculate, it is 120 into 10 raised to 3 divided by 400 into 300. We will get this as 1 Newton per mm square. Okay, so now we can alternatively write the equations for the stresses at the different points. As if we look, this is our quadrant system. Okay, and we had the load here, so here we have plus plus, and here we have um, this, here we had plus minus, and here we had minus and plus, and here we had minus minus. So this was the equation, I mean this was the signs of the stresses. So sigma b has already been calculated. Let us calculate the other stresses. So sigma a is going to be the direct stress, then plus the bending stress about the x-axis for the point A, minus bending stress about the y-axis for the point A. So this is going to be, this is 1, then sigma bx is plus 0.6 and sigma bya is minus 0.6. So we are going to have 1 Newton per mm square. Now similarly sigma c, if you calculate sigma c, sigma d minus sigma bx about the point C, and the next term is plus sigma by about the point C. So we are going to have 1 minus 0.6 plus 0.6. We are going to have a net of 1 Newton per mm square. And lastly, sigma about the point D. So we are going to have again sigma D. We are going to have negative sigma bx about the point D minus sigma by about the point D. So we are going to have 1 minus 0.6 minus 0.6, that is going to be equal to minus 0.2 Newton per mm square. So these are going to be the stresses at the different point, and all the negative signs are going to indicate that the stresses are tensile, and all the positive signs indicate that the stresses are compressive in nature. So this is one type of problem that you can expect from this chapter. Let us do one more type of problem. which we can expect in this. So what we are having is, we are having a column, and there is a load that is acting at an eccentricity of 10 mm, and in the cross section, if you look, the cross section is going to look like this. So this is your x-axis axis, and this is the y axis. So we have 75 mm as the dimensions of the square is 75 mm, and then we have a hollow part inside, and the dimension of the hollow part is 37.5 mm. So this hollow part is having a diameter 37.5 mm. Okay, that is the diameter. Now what we have to understand is, the load is assumed to act with a single eccentricity. Okay, so the load is supposed to act here. There is no eccentricity about the y-axis, there is only eccentricity about the x-axis. Now what we are told is, we are told that the maximum compressive stress is 80. So sigma max that can occur is 80 Newton per mm square. So for a maximum compressive stress of 80 Newton per mm square, we need to calculate what is the maximum value of load that can be carried by this column. Okay, and as you know, the stress at any point, okay, is going to be a combination of the compressive stress as well, the direct stress, as well as the bending stress. So since the eccentricity is on this side, what is going to happen is, the bending is going to take like this, and all the points on the right half of the x-axis is going to be under compression, and all the point on the left half is going to be under tension. Okay, now we also have to understand that the shaded portion is the exact column, and the circle is not available as part of the column. Okay, now what we have to understand is, the maximum stress is going to be at all these points. Okay, the maximum stress is going to be at all uh, these points which are at a distance, at equal distance from the from the x-axis. So the maximum stressed points will be the stresses along this side of the column, because they are at a maximum distance from the x-axis. So let us try to calculate what will be the stress at this particular side of the column. So if we try to write an expression, so let us say sigma is going to be equal to sigma d plus the bending stress about the x-axis. Okay, and let us take some arbitrary point. Let us take this point as some point A. So about the point A, so this is sigma A. So it is going to be equal to, sigma d is going to be equal to W into E. E is going to be 10 mm divided by the area. The area is going to be, we have to take the net area. So the net area is going to be area of the square minus area of the circle, pi d square by 4. So this is going to be the net area, and this area can be calculated as, so if we calculate this area, it comes out as 4250.5 mm square. 4250.5 mm square. So divided by 4250.5 mm square plus, we are assuming W is in Newton. Now sigma bx, so that is going to be equal to, again there is a slight mistake here. We do not require this E here, we only require the load divided by the area, that is W by A, plus we are going to have the moment is going to be W multiplied by E. So W into E is 10 mm divided by, we have to have IXX. Now IXX has to be, again we are having a composite section, so IXX is going to be, IXX is going to be equal to, both are having the same centroidal axis, so IXX will, of the composite shape will be IXX of the rectangle minus IXX of the circle. Okay, so this you can get it as BD cube by 12, or since it is a square it will be a raised to 4 divided by 12, and since this is a circle this value is going to be uh, pi d raised to 4 by 64. So pi d raised to 4 divided by 64, this will be the value. So if we try to substitute it, we can get the value of Ixx as, let me check the value. It is going to come out as 2539695.74 mm raised to 4. So if we substitute that value of Ixx here, it is going to be 2539695.74. It is in mm raised to 4. So multiplied by Ymax. Ymax is the distance from the x-axis to the extreme point, and that distance is 75 divided by 2, which is 37.5. So 37.5, 75 divided by 2. So this is going to be the value. Now this is the expression for maximum stress, and this we have to equate to 80 Newton per mm square, which is the maximum value of stress. Okay, so the only unknown in the equation is W, and if we simplify this expression we can get the value of W. So if we try to simplify it, we will see that the value of W comes out as, the value of W will come out as 216877 Newton, or you can write it as 216.87 kilonewton. So this is the value of W. That is the maximum load this column can take. So with this lecture we complete our discussions on the direct and bending stresses on short columns. We will see with another problem in the we will deal with the long columns in the next lecture. We'll stop for today. Thank you.